that should be exciting. Should be neat. Okay, so circle numbers. Let's dive in here. All right, so basically the idea is just like with a lot of these challenges, picture's worth 1,000 words. It's very nice to see this picture here. So basically the idea is that we're given integer numbers from 0 to n minus 1, where n is a number supplied in the problem, and it's always going to be an even number. Anyway, the idea is it's written along a circle, all the numbers in an increasing way. The distance between any two neighboring numbers is equal, so they're like evenly distributed along the circle. You know, it's not like 0 is here and then 1 is like way over here and then 2 is right next to it. Like they're evenly distributed, and that's going to be important for the first algorithm we're going to use here anyway. So basically, what we want to tell, also 0 and n minus 1 are also neighboring. So like in this case, 9 and 0 are right next to each other as well. It's cyclical, right? It keeps going around like a modulus. And maybe that's a hint. But anyway, we'll see. The main thing is that what we want to be doing is this. We're going to be given a number. So first number in this case was 2. And we want to find the one that's radially opposite to first number. So we would say, well, basically what we're going to do is imagine we've got the center of our circle over here. We want to draw a line segment that goes through this point, through the center, and then all the way to the opposite, the radially opposite point. So 7 is what we should return as our answer. Okay, cool. So then, let's say like if 9 was our value, if 9 was our first number, then again, we'd go through the center, just go opposite, and we'd get 4. Okay, so that seems good. Now, by now, if you've been watching my videos, you know the way I like to start these things. I want to start with the most naive interpretation of the problem. In this case, that means I want to start by drawing the circle of numbers. I want to create a circle of numbers. The thing is, like, in JavaScript, we've got arrays, we've got matrices and stuff like that. We don't really have, as far as I know, we don't really have an easy way of representing a circle, certainly not in a very visual way. So I'm actually going to use a grid for this. So I'm going to make like, a Cartesian plane kind of thing. And then we'll try to use some kind of like polar coordinates business in order to actually plot the points here. So this is going to be fun. We're going to actually make the circle of numbers. Oh boy, I can't wait. All right, so we're going to start by determining our radius. I mean, it's going to be a circle after all, right? So we want to make our radius big enough, but not too big. So maybe we'll start with something like 5, and we'll see if that's good enough. I mean, something to notice, and I didn't show this before, but the numbers we're going to get for n are only going to be between 4 and 20, okay? So it's going to be an even number. It could be 4, it could be 20, it could be any even number in between, but it can't be above 20. So I think probably a radius of 5 is going to be good enough, because it means we're going to be looking at a plane where we're going 5 to the left, 5 to the right, 5 up, 5 down. So it's going to be like an 11 by 11 grid, sort of. So let's see. We might as well do that. Okay, so we'll create the grid. Wait a second. How did so many spelling errors happen at once there? Oh boy. All right, so we're going to create the grid, and we'll do that like sort of the way we did it before. Let grid be this empty array. We'll say for let I be assigned the value of 0, I is less than or equal to radius times 2. Okay. Why radius times 2? Well, because it's going like 5 to the left and 5 to the right as well. So basically the rows should have not just 5 elements, but they should have 5 to the left and 5 to the right, plus the one in the center. So it should technically be 11, and that's why I'm putting the less than or equal to. I could also just say radius times 2 plus 1 and make it a strictly less than. That would work too, but it doesn't really make a difference. Okay, and we'll say let row be assigned the value of this empty array for, I don't need a space there, for let j be assigned the value of 0, j is also less than or equal to radius times 2, and j plus plus. So then from there we'll say row dot push. What do we want to be putting in here? I guess just like a space for now. Might as well. And then for the grid, we're going to push the row onto that. So then let's say return grid. And actually, before we do, let's just say grid, wait a minute, grid at radius is assign the value of this x, just to sort of mark the center. Okay, so there we go. That's kind of our grid. This is like our playing field here. This is what we're going to be working with. So, okay, looks good, looks good. But that's not the end of it, right? We've got to do some other stuff to this. So we've already marked the center, and maybe I want to make a comment for that. Mark the center. Wow, my spelling is like on another level today. Okay, so a lower level specifically. All right, mark the center, and then, okay, basically what I want to do is I want to get all the angles of these things. So I sort of want to like divide it up into sectors. So let's make this orange. Let's get a nice orange color. Orange is, you know, a citrus fruit. It comes in sectors, so this is appropriate. Whoa, whoa, these are not proper line segments here, pal. Okay, so yeah, I have to apologize for this diagram. But anyway, the main thing is what we're trying to look at, and let's get, I guess, a green. That's also a citrus fruit color. So what we want is, we want to know what this is, right? We want to know theta, like how big each sector is going to be. And then we're just going to add that on. So, you know, like if that's theta, then like this here would be like 2 theta, or like, you know, that would be 3 theta. So we're going to figure out like how big of an angle there is for each segment, for each sector. And then we're basically just going to make an array that has n many of these things, and it's going to look at all the angles that we should be looking at here. And that's going to help us because, like I said, you know, polar coordinates. Now, I was planning on using radians for our angle. Does anyone have a preference? Is there anyone here who like definitely wants to use degrees? Because if you want to, that's fine. Like it's not a big deal or anything. But if we do use degrees, we're going to have to convert them to radians anyway, because that's sort of like the expected value for JavaScript. JavaScript is expecting radians. So, you know, like if we're using sine and cos and stuff like that, if we use any trig tools in JavaScript, it's expecting our angles to be radians. And so we probably want to use radians. Like I said, we could use degrees and then convert to radians, but maybe we'll just stick in radians. And there's actually a time when I was in first year university, I was taking a linear algebra course. And this is like, you know, I wasn't like super into math at this point. I was doing an engineering degree at the time. And eventually I switched into math, but that's another story. The point is, I was in like a discussion group, you know, we're going over some questions, and one of them had to do with angles. And so I gave an answer, and it was like 37 degrees or something like that. And the teaching assistant was like, yeah, that's the right answer, but what do grown-ups use? And, you know, she was referring to radians. So I guess there's this perception of radians being a little more mature, being more of a proper way of talking about angles. I mean, technically, radians are the angle, you know, like radians are the proper way of looking at the angles, in the sense that like they sort of tell you what the length of the arc would be for a unit circle, as opposed to degrees, which, like, if you've ever wondered why there are 360 degrees in a circle, it's just because 360 is a number that has a lot of factors. You can divide it up into a lot of different ways. You know, you could say 360 divided by 2, 360 divided by 3, divided by 4, divided by 5. Like, it has lots and lots and lots of factors that we can use to cut it up in a lot of ways. So that's convenient. It's the same reason why we have like 60 minutes in an hour or 60 seconds in a minute. 60 has a lot of factors, just like 360. Well, 360 has even more. But anyway, the point is, we're going to use radians here, I think. I don't see anyone in chat really requesting degrees or anything like that, so we're going to use radians. So basically, we're going to figure out what's the size of each sector. So let's say rads per segment. Okay, rads per segment. And it's going to be equal to 2 pi. So we've got this nice built in here, math.pi. And keep in mind, 2 pi is like a full 360 degrees. Okay, so we've got 2 times math.pi. And we're just going to divide that by n. Okay, so basically radians per segment, well, it's the total number of radians in the circle divided by how many segments there are. Makes sense, right? We're just dividing it up evenly. So, and in fact, maybe not a let for that because it's something that's not going to change, right? So it might as well be a const. And then we're going to let angles be this empty array, and we're going to fill it up. We'll say for let let I be assigned a value of 0, I is less than n, I plus plus, and we'll say angles dot push I times radians per segment. Okay, and that should give us our angles, but let's just make sure that it does. And actually, when I return this, it's probably not going to look very nice. Yeah, okay, it's not looking very nice, but is there the right number of them at least? We have 10 segments, so we should expect 10 angles. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Great. All right, so it's the right number of them. I guess I'm convinced, you know, that these are the right numbers. Who knows? Okay, so those are our angles. Now, why is it going to be useful to have our angles? Well, because we're basically going to be able to use the angle and the radius to convert from polar coordinates to Cartesian coordinates, which is what we're dealing with on our grid, right? So let's maybe let's write some functions for this, because this is a sort of thing we're going to be using a few times here anyway. So we'll say get x, and this is going to take in an angle. Right, we're going to convert the angle to an x value, and then we'll convert it to a y value as well. We're going to round this value because keep in mind our indices on our grid are whole numbers. We don't have like grid at 1.5. It's got to be whole numbers. So we're going to do math.round, and then we want something. Like keep in mind on our grid, and I'll just run this so we can see our grid. Take a look at it. Okay, there we go. So on our grid, keep in mind the center is at radius. Right? So we want to do something like radius times math.cos of angle. This is what's going to give us kind of like the x coordinate from 0, but keep in mind our 0 is already at radius here. So we need to add radius onto this whole thing. So we've got radius to get us to the center, and then from there, radius times math.cos of angle, and that's going to give us sort of like the horizontal version. So like what I'm trying to say is this: if we had something sticking out like that, right? Like basically we would have this angle here. This is theta. We know the radius of this thing, that's r, let's say. This function we just wrote, it'll give us the x coordinate. So it'll give us the index, basically or one of the indices of where we want to put our point. Great. Okay, so let's write another function. It's going to be called get y, and it's also going to take angle as an input, and it's going to do something so similar to this last one. We already talked about why we need to add the radius on, but you know, if you have any questions, let me know. And we're going to multiply that this time by math.sine of angle. So keep in mind, in trigonometry, cos is going to give you sort of like the horizontal component, whereas sine is going to give you the vertical component. So again, you know, like let's say we were talking about something that was going to stick out like this, let's say, or no, better example would be, oh, I need to scroll up, so I need to close that. But yeah, and in fact, let's get a better color in here. Okay, good. So let's say we're looking at something like this, right? That went out this way. Now the idea is that when we take cos of this angle, we would actually get something negative because the horizontal component is negative, whereas when we do sine, we'd get something positive, but quite small. Okay, and that would form a right angle triangle, but we don't need to get into that right now. The main thing is we'll get our horizontal and vertical components using get x and get y, respectively. Okay, so now what we want to do is, let's see. Okay, let's actually do the circle of numbers. Okay, so we're going to do a loop. It's going to say for let num be assigned a value of 0, num is less than n, and num plus plus. Okay, so num is the actual like the 0, the 1, the 2, like all those kinds of things. Okay, so then we're going to say const angle is assigned the value of angles at I. I mean, for a minute there, I was just wondering, like, you know, could we do this with just like for let angle be assigned the value, or sorry, for let angle of angles or something like that? But there's a reason I don't want to do that. It's because I do want to use the index, and in fact, it's not even I, it's called num, and I want to use it down here. So basically, let's get our x and y. So let's get x of angle, and const y is going to be get y of angle. Okay, and then basically what we want to do is just say grid at x at y is num. But we want it to be a string version of num, not for any real particular reason, mainly just because we've got quotations around all these things, and if we didn't use a string, it wouldn't have the quotes, and so it'd be 2 characters more narrow, and it would kind of change the size of the grid, which I feel like that bummed me out. So we don't want to do that. Okay, so we're going to run this thing, and look at that. Folks, we have a circle of numbers. Let's make this a little bigger so we can admire it. Look at that. It's a circle of numbers. It's the circle of numbers that we're looking for. Isn't that cool? I think that's pretty cool. And it even works for like a lower number. Let's even get, okay, the highest possible that could be is 20. And if we start at 1, it should take us to 11. We'll actually check on the functionality later, but I just want to see. Oh, and would you look at that? It's creating the circle of numbers. Now this one does look a little ragged on the side here. That's just because we have some double-digit numbers here. So I guess nothing we could do about that unless we actually want to pad these numbers. But then, yeah, that's getting kind of complicated. The main thing is that they're all fitting. And so a radius of 5 is big enough. Whereas something like a radius of 3, I'm assuming they wouldn't all fit. They would probably have some numbers being overwritten. And yeah, notice how it goes 0, 1, 3, because I think 2 would normally belong here. So, okay. We could even make it bigger if we wanted to, make it like a 7 or something like that. But no, you know, it's getting a little messy. Going on the next line. It fits them all quite nicely, and it's going to work for something like this as well. But, you know, I think 5 was fine. I think 5 was like good enough. I think it was right in the middle there. It was, actually, I guess we don't need to make that much smaller. Okay, so yeah, I think that was a good number of them. So maybe instead of return grid, let's just do a console.log on the grid, just so we can still see it, because, you know, we like it. We're very proud of it. It looks beautiful. But it's not really what we want to be returning. What we want to return is the opposite number, right? So let's get our new angle, okay? So let's say const original angle is going to be angles at first number. Oops, first number. Yeah, angles at first number. So this is maybe giving you an idea of like why we did it this way, like why we put all the angles inside of an array. I mean, there are a few reasons, like it helped us out up here for actually putting these numbers inside the circle of numbers or on the grid, but also it's helping us to get our original angle from this original number. Now, why do we want that original angle? Well, it's because we want to get a new angle, which is going to be original angle plus math.pi, not math.po, math.pi. Okay, great. And that's a constant. That's going to give us, you know, exactly like our 3.14159, etc. And okay, so that's our new angle. Now from there, all we need to do is this. Oh, this is the part that I love. Okay, so const x and y is going to be, or should I do it this way? Maybe not. I'll just do them separately. I'll say x is going to be get x of, no, not angle, new angle, new angle. Notice how it suggested new there. That's because that's always going to be a keyword. It's a built-in for new objects, which I think we've used. But anyway, so we've got our x and our y for our new angle. I guess I could have called them like new x and new y or something like that. But the main thing is basically we're starting by saying we're looking at the number, I don't know, what was in this first one? 2. Okay, so we're saying here's 2 over here, right? What was the angle that it took to actually get from 0 to 2? What was the angle in here? And then we say, okay, we want to add pi to that angle. Oh, and by the way, I guess I should have explained this part here. When we're talking about radians, pi represents like a 180 degree angle, you know? So like this right here, that angle, that's pi. They call that a straight angle in math. It's not obtuse or acute. It's a straight angle. Okay, and then it goes across here to find 7. So basically what I'm trying to say is we're starting with this angle, like we're starting with this angle in here. This is like theta. This is our original angle right here. And then we're adding on to that pi. That'll give us a new angle, which represents like all of this. And it would take us directly to the 7 here, which really is what we're looking for, right? That was the answer. Well, I guess I'm blocking that out, but believe me, it was the 7. Okay, so I'm going to close that for now. And what I'm going to do is just return grid at x at y. And there's just going to be one problem with that if it works, and it's that it's a string. We want the integer value, so we're going to do parse int on that thing. You can see our nice circle of numbers in the console log down there. Ooh, very nice. So we get 7. Look at this. We're passing all the tests. We're passing all the tests, even the custom test. This is great. Okay, so I'm gonna make that a little smaller, quite a bit smaller actually, just because I want to take a look at where we've come from and try to appreciate what we've been able to accomplish here, because it's something. Anyway, okay, so we had our radius, we had our x, and we made functions to get our x and our y, and this is basically like converting from polar coordinates to Cartesian coordinates. So I'll just say functions for converting from polar chords. Great. And then after that, we made a grid. We marked the center of the grid, and I guess I should say over here, generate all the angles. I feel like I've misspelled every single comment I've made so far. Okay, so right, we generate all the angles, so we figure out what's the angle for every number. We then put those numbers on the grid by converting our angles into Cartesian coordinates using the functions we had above here. And notice we use those functions again later down here, which is, you know, why they're functions, because we don't want to not repeat ourselves. Okay, console.log grid, that's just for fun, so we can see it. It would work without that, but it's nice to see. And then this is find the new angle, and then from there, what number is at that location, right? That's what we're returning. Find the new angle and get the number. Let's just say that. Okay, so let's submit that. Let's see if it passes all the hidden tests and it gets us through. Beautiful. Now that feels great. Congratulations on being here to help me celebrate this accomplishment. I like this algorithm. I like it a lot, actually. I like how literal it feels, you know, like the problem asks us to make a circle of numbers and find the opposite one. And yeah, that's exactly what we did. We made a circle of numbers and we found the opposite one. So I just like the look of that circle of numbers. I think that's pretty cool. But there's a reason I called that a naive interpretation. We probably don't need to do all this. It's probably massive overkill, just like what we saw on the chess problem. So massive overkill. Okay. So what would be not massive overkill? Well, let's find out. Let's think about this for a moment. So let's grab a cool color. You know, we haven't used brown yet today. Let's get brown in here. Okay, nice. So we're starting here, right? Now, how many numbers do we want to go around before we get to the 7? We're going to go 1, 2, 3, 4, 5, around to the 7. Okay, and I guess that kind of makes sense, right? Because if we went 10 units around, we'd end up at the same spot. And we want the opposite spot. So 5 is half of 10. It's half of n. So could we get away with just adding n divided by 2 to this? Like, is that going to be enough? Could we just add n divided by 2? Is that it? Return first number plus n divided by 2. Is that going to work? Not for all of them. It worked for some, but not all. So if we look at the second one, notice the first number here is 7. And that's what we had. Where'd that brown go? Oh, that was a good color. Okay, so we had 7 over here. And again, we're just adding 5 to it, right? We want to go around. If we add 5 to 7, we don't get 2, we get 12. We don't want 12. So basically what we can say is, all right, make our new number the result of this, right? So we'll say, let next number be assigned the value of first number plus n divided by 2. And then we'll say if next number is greater than n, or actually if it's greater than or equal to n, that would mean it's too damn big. So we would need to say next number minus equals n. I'm going to subtract n from it. And then at the end, we're going to return next number. Sorry about the traffic today. It's bad. Anyway, okay, great. That's enough. That's enough. Can you believe that's enough? Look at all this. Look at how long this thing was. Oh boy. And that's all we had to do over here. So that passed all the tests. I can't believe that. That's, in one sense, it's amazing. In another sense, it's infuriating because we did so much work and it feels like, you know, maybe it was a waste of time. Well, no, I wouldn't say it was a waste of time because we had fun, we learned something, and we had fun. So that's the main thing. So let's paste that in. Is there another way we could do this? Well, as it turns out, yeah, there's another way we could do this. You know, let's say instead of going around the circle this way and getting to the 7, maybe we'll say, oh no, actually I want to go around the circle this way and get to the 7 from the other direction. Okay, so then we'll say subtract n minus 2, and if it ends up being less than 0, then we'll add n to it. And that should give us basically the exact same thing. Now, this seems almost like exactly the same. You might wonder, well, why did I bother showing you this one? And the reason is actually really, really simple. It saves 1 byte. So basically, there's one character that you don't have to use here. You can do this in one fewer character. So if you were trying to do a code golf or something like that, you know, that's the sort of thing you might want to consider. The other thing is, I kind of like the way this is just comparing it to 0 as opposed to n here. Like it's one fewer reference. So it's like one more thing that's not going to change with a different value of n. Anyway, there's probably another way to do this. I mean, look, we're talking about a situation where we're maybe having to subtract some number if something is too big. That sounds familiar. It sounds kind of like what we're talking about is a situation that would be appropriate for a modulus. Remember, the remainder if you were to divide by that number. So if we were to do the 7 here, so we do 7 plus 10 divided by 2, which is 5. That gives us 12. Divide that by 10. What's the remainder? It's 2. Okay, great. Whereas something like this, we started with 2. We add 5 to it. We get 7. What's the remainder when you do 7 divided by 10? Well, 7 doesn't fit into 10, so the remainder is still 7. So that's all we had to do. This is it. This is the entire code. That's a single line, and it's not even a very complicated line. That's unbelievable. I mean, compare that to this. I could go on all day about that. But anyway, point is, it's telling me I have too many ones. Okay, that was the problem. All right, great. So cool. That was fun. That was a good one. I like that one. I think that out of all the ones we've looked at so far, I think this is the one where we got the biggest savings, so to speak, from our first algorithm to our last algorithm. Like that's just absurd. Anyway, I don't want to blab on about that any longer. I guess let's wrap it up here. I guess. So did I submit it? I hope I submitted it. Hopefully this passes all the tests. Actually, I don't know if we even checked. Okay, great. So 5044 is the one to click if you want to take a look at this. This was massive overkill, but anyway, I won't go on about that anymore. Let's wrap it up there.